Okay, so any questions? Last class we are discussing about this one cache with n-way associative cache. It is like set organized in the form of sets. Cache organized in the form of sets, and the sets have the multi-association, like n-way association. Set may have the like multiple entries and have fully associative, right? And n-way associative. So all these things we discussed in the last class. So any questions on that? Okay, then okay, let me share the presentation. So so if you remember, so we had discussed this in the last class in case of set associative cache organization. So what will be the overall structure, or how the cache is organized, and then how the cache is indexed, or how the cache is accessed. So all these things we discussed in the last class, and here this is the scenario where it is four-way set associative cache. It means that each set contains the four blocks, and here in this scenario the block happens to be one word, and it may have the multiple words also. 4 words or 4 blocks, and that means each set contains the 4 blocks. Now we have a flexibility, right? Where in case of direct mapped cache and all, where each entry of a cache holds only one block. So therefore, if any new block it is referring, so if it is not there, then you have to replace that. But here we have some flexibility where a set contains the 4 blocks, and usually from the this physical address, from this address, you can able to come to know that a block may present in this set, right? If it is not present in this set, then it should be there. So therefore, we have to see that if there if the entire set is full, then we have to replace one of them with by fetching the new block. Otherwise, if there is some empty space is there, then without replacing, you can able to fetch and you can use that empty space for this new block and all. So all these things we discussed in the last class. And since from these 4 blocks, we need to pick up the desired block. So for that purpose, so these lines, whatever here, the output of these these 4 comparators and all. So these outputs are directly can be used as the signals for picking up the desired block from here and all, right? Because this is there are 4 blocks are there. Out of 4 blocks, only one block is the one which is required. So that can be picked up from by using these control lines and all. Because these control lines will inform you that actually which of the block is the desired block and all. So from this you can able to pick up out of these 4 blocks, one will be picked up. So then as we have seen here, in case of this set associative cache, so what is the replacement in general, like in case of cache? So what is the replacement policy? It means that suppose when the memory access is given by the CPU, if it is not present in a cache, and in that case you need to fetch the block from the main memory and you have to place it into the cache. In that case, suppose the cache entries are filled up, then you have to replace that. So how do you replace that? What is the replacement policy? And in case of direct mapped cache, there is no choice at all. That means if there is a cache miss is there, means at that location we need to fetch the desired block and have to place it, because there is only one space or only one block can be accommodated in the particular entry of a cache. So therefore there is no choice at all. So it has to be replaced if there is a miss in case of direct mapped cache. Whereas in case of set associative cache, we have flexibility because the set may contains the multiple entries, as we have seen in the previous example, like a 4-way associative. It means that set may contains the 4 blocks. So if there is an empty block, then without replacement, you can able to fill it up. And if all 4 blocks are filled up of a set, then if a miss occurs, then we have to choose among those 4 entries, we have to choose the one entry, one of the block can be replaced. One of the block will be replaced with the new block or fetched block and all. So in that case, we have to see that what is the policy, which block has to be replaced. So the first one here I mentioned that if there is any non-valid entry, it means that there is an empty block is there, empty entry, the entry with empty block, then anyway there is no need for replacement. The fetch block can be placed into that. So that will be known by using a valid entry, right? And the other one is that, like suppose for example, if all blocks are filled up, then we have to replace one of them. So for that we can use the policy like least recently used. So it means that out of these 4 blocks, so we have a mechanism to analyze or to judge that which of the blocks are recently used and which of the blocks are not recently used. So among them, the block which is not recently used, so that block can be picked up for replacement, right? So for analyzing that or for maintaining this status of least recently used one, so if a set contains the very few associations like two-way association, four-way association, then you can able to do that. You can able to manage, or you can able to manage that, like out of these 4, which is recently used, and you can able to analyze that. You can, by using some specific bit with that, you can able to do that. And but it is also complex if the set contains larger number of entries, right? Suppose for example, if set contains 64 blocks, for example. So in that case, again, maintaining them within a set, again, maintaining among the 64 blocks about its history, like which one is used, when it is used. So you have to tag some time index or counters kind of a thing, how many times it has been used. So all these things has to be maintained. So it becomes complex if the number of the set size is larger. So in that case, people have explored along with the least recently used, there is another approach known to be random approach. Random approach means just pick up randomly one of the block. And this holds good. The random way of replacement is almost the performance is similar as that of the least recently used if the set associativity is larger. That means if the set contains a larger number of blocks. So in that case, whatever the least recently used will perform, almost if you use the random way of replacement policy is also performing almost close to that performance and all. It means that even the random replacement also works better in case of when the set size is larger. That means the set contains a larger number of blocks. So in that case, both random and as well as LRU will perform more or less similar and all. So it is statistically in the mains. So these are the various replacement policies that can be used in the cache, because direct map to cache there is no policy at all. And in case of set associative, we have this one, set associative or like fully associative. Then you can make use of these policies and all, like least recently used or a random pickup, random replacement and all. Random replacement usually used in case of fully associative, where only one set with all entries becomes a part of that. So therefore, as it was mentioned here, the random replacement will perform almost close to the least recently used. You can use, but the sets with having a lower number of entries, you can use the least recently used, which performs the optimal performance, which give you optimal. Okay, yeah. Yeah, then this particular numerical example will provide you that, like what will be the tag size by varying the number of sets and with the different set associatives and all. So what is the tag size, how it varies and all. So this was explained here. This was described over here using this numerical example where the solution is also provided. So you can able to go through that. It is very easy to follow, no difficulty at all. So please go through that. You can able to understand that. So in case of set associative, as the number of sets increases or a set having associativity increases and all, how the tag bits were varies and all. So all these things are given here with a numerical example. It will make you provides you more clarity on that. Then the next one is that actually in the cache itself, there is, like, so far we discussed about a cache and a main memory. And for improving the performance, and also you can use, instead of one cache, you can use the cache at multiple levels. Like now, right now we have a cache and then the main memory, and CPU directly accesses the cache initially, first attempt, and then if it is not there in the cache, then the data or instruction will be fetched from main memory to cache, and then it will access. And instead, directly going for a main memory to cache, if we can able to keep some other caches with varying performance characteristics and all, then the miss penalty can be reduced. That was the idea. Because we know that cache can be accessed, cache entries can be accessed in less than a nanosecond, or within a clock cycle itself, you can able to access the cache contents, right? But the moment once you want to fetch the contents from a main memory, it takes the number of cycles that are required will be order of around 100. So during that time, the CPU has to be idle, or CPU has to be stalled, and we need to wait for the desired data to be fetched from main memory to a cache and all. So that means miss penalty is more. So to overcome that, instead of having one cache, you can have a cache with high performance, with a very fast access time close to the CPU. And there are other caches you can able to keep, one more cache at the next level, second level, you can keep, where which are if it is a cache miss at a very higher level, then it may check the cache at the next level. The cache at the second level will be higher than having higher capacity compared to the cache at the higher level and all, cache at the first level and all. So likewise, instead of directly going to the main memory, you can have some intermediate caches at different levels. So with that, the miss penalty can be reduced. So we can able to see here in this example, like you can see that in the next example. So here, the primary cache is nothing but it's attached to CPU. It will be small and faster, obvious, because if the cache is larger, then access time will be increased, right? And so therefore there will be a trade-off. If you make a cache with a larger number of entries, then access time will be larger. So with that, it tries to stretch the CPU cycle. That means CPU cycle period should be larger enough is required. So therefore, like you can say that, so therefore the clock rate has to be reduced. So these are the various impacts on that. And the level 2 cache, that means instead of the primary cache, there is one more cache you can keep. Level 2 cache services the misses from the primary cache. That means if the cache, if the first initial access, the CPU do perform on the top level cache or cache at level 1, if it is not present, then the level 2 services, level 2 provides that. That means level 2 provides, if there is a miss in the level 1, so that can be accommodated, will be in the level 2 instead of going to the going to the main memory and all. So it services the misses from the primary cache and all. So therefore, to perform that, obviously it should be larger enough. And since it is a larger and also it will be slower because access time will be larger. And but still it is much faster than the main memory. Like for example, a cache at a primary level may take half nanosecond, for example. So in that case, a cache at a second level 2, it may take about 5 nanoseconds, 10 nanoseconds, something like that. Right? Whereas the main memory may take around 100 nanoseconds. Instead, it will be much lesser. So with that, the penalty will be reduced. Right? And the main memory, anyway, the main memory will be there to service the L2 misses, or if suppose there is one more cache like L3, something like that, L2, L3, and so on. Right? And yeah, we'll see this numerical example, then it will be clear for you. Suppose, for example, you have a CPU with only one cache, only primary cache, and afterwards you have main memory. So in that case, for these specifications, for example, a clock rate equals to 4 gigahertz, for example, and the CPU, if it finds the data or instruction in the cache, it takes about for executing instruction, it takes about one CPU cycle, like one CPU, one clock cycle and all. Like the clocks per instruction, clock cycle per instruction, it's one. It means that if the data or instruction is present there, and then for executing instruction, it takes about one clock cycle, right? And as we know that since it's a primary cache, so assuming that the miss rate equals to 2%, for example, miss rate equals to 2%, and the main memory access time equals to 100 nanoseconds, it means this is the miss penalty, right? Because if there is a miss rate, if there is a miss in the primary cache, then we have to fetch that block from the main memory to the cache. So therefore it takes about 100 nanoseconds roughly. So therefore the miss penalty is like 100 nanoseconds, and here the clock cycle is clock rate is 4 gigahertz. So the clock cycle equals to 1 by clock rate. It gives you about 0.25 nanoseconds. So 0.225 nanoseconds is a 1 clock period. So therefore here main memory access time is 100 nanoseconds. So therefore the number of clock cycles that are required for a miss penalty equals to 400. 400 cycles are required for a miss penalty for every miss. So therefore the effective CPI will be, if effective CPI in case of 2% miss rate with only one cache will be 1 plus 0.02 times 400 gives you 9 cycles. It means that on average, using this configuration, we have one primary cache with the 2% misses and a clock rate of this much, and this is the miss penalty. If this is the scenario in these specifications, the average CPI or the effective CPI, the clocks per instruction, cycles per an instruction execution, it takes about 9 cycles and all. It takes about 9 cycles for a larger program if you take that. And so this 9 cycles is too much, because if it is if it is ideal case, it's only 1 cycle, right? And in case of this miss rate of 2%, it stretches the CPI to like 9 cycles and all. So now we'll see that in case of use a multi-cache, like instead of 1 cache, if you use the 2 caches, where now if you add level 2 cache, where the access time of level 2 cache will be 5 nanoseconds, whereas the access time of level 1 cache is only 1 cycle. 1 cycle means 0.25 nanoseconds, whereas here is 5 nanoseconds, and a global miss rate equals to 0.5%. So global miss rate means here if a miss occurs, the miss for that miss, the data is not present in the primary. Miss means actually the primary cache, the data is not present. Then it will go to the level 2 cache and it will check for that. And if the data is also not present in level 2 cache, then it has to go to the main memory and all. So here the global miss means here the miss across all the caches. It means global miss means the 0.5% of the times the data is not available in any of the caches and all. So it has to go to the main memory and it will fetch the desired content and all, right? So here in the problem, the same problem, we have seen that there is a 2% misses at the primary cache, right? And a global miss of 0.5%. It means that when the CPU tries to access the data in the primary cache, 2% of the times or the 2% of the instructions data where the contents are not available in the primary cache, but some of them are available in the secondary cache. But 0.5% means 0.5% of the instructions or data which are not available both in primary L1 cache and L2 cache also. So therefore it has to go to the main memory, it has to fetch that. So if you look at that, if you look at the L2 cache, the performance of L2 cache, or you can say that the hit rate of the L2 cache will be how much? Because here you can see that the L2 cache will be accessed only in case of miss in the L1 cache. And we know that in L1 cache, the misses are 2%, right? And global miss equals to 5%, 0.5%. It means that, so the 2% is a miss rate. Out of that, 1.5% of the misses will be taken care by L2 cache, and the remaining 0.5% they are not available at the L2 cache. So therefore, they had to go to the primary memory or a main memory to fetch the data and all. So it means that in case of L2 cache, the miss rate is 25%, or you can say hit rate equals to 75%. Hit rate equals to 70, because 2% of the misses are there. Out of the 2.2%, 1.5% is served by the L2. They are available at L2. And whereas 0.5% they are not available at L2. So therefore they have to go to the primary memory. So that way, if you look at the L2 cache, you can say that the hit rate equals to 75%, whereas the miss rate equals to 25%. It appears to be like much larger, very large. But you have to note that the L2 cache will receive the access only upon the misses from the L1 cache. So that way, even the 25% miss rate is also reasonable enough. We can able to see here. So therefore, the penalty at the L2 cache will be like penalty from the L2 cache will be like 20 cycles, because the access time of L2 cache equals to 5 nanoseconds. So we know that the clock period equals to 0.25 nanoseconds. So with that, 20 cycles is the penalty when it reaches to the L2 cache. So when it reaches to the main memory, the penalty is 400 cycles that we have seen. So therefore, by including the L2 cache, and the overall penalty or overall CPI will be 1 plus 0.02 times 20, because for the 2% of the misses and all, so they will come to the L2 for service, for their service, right? They will come to the service, and then 0.5% of them they will reach to the primary memory and all. So that way 1 plus the 2%, like there's nothing but 0.02 into 20. 20 is nothing but the penalty offered by the L2 cache access time, and 0.005, that's nothing but 0.5% of the global miss that will reach to the main memory. It's 400 cycles and all. So this altogether will be 3.4 cycles. So it means that by introducing L2 cache, the CPI, effective CPI, will be reduced to 3.4 from 9. Earlier we have 9 by using only one cache, and now by introducing one more cache, where with the miss rate, with the global miss rate of 0.5%, you can able to see that the CPI, effective CPI, will be 3.4. So with that, you can say that the performance improvement will be like order of 2.6 times, right? So this way, if you can able to add more and more caches and all, then the performance can be improved. But again, there will be a trade-off and all, because cache will be like it's expensive one, and not only that, for every cache and all, it will take some access time also. So we had to see that how many levels you can able to go for, like in view of various constraints. Yeah, like. And yeah, these are the various considerations. The primary cache is actually here, we'll try to focus on the hit time, access time. The primary cache, we need to mainly focus on the hit time. That means we have to see that the primary cache, where the access time should be very fast, because whatever the high clock rates and all, it should satisfy with that. So therefore, we had to see that the primary cache, the access time should be minimal, so that a shorter clock cycle can enable to access, can be sufficient to access the data from a primary cache and all. And the L2 cache, where here we have to see that the miss penalty should be minimized, and the miss rate offered by L2 cache also can be tried to minimize and all, so that so that it cannot go to the access should not be missed out from the L2 cache and all. The focus on low miss rate, and to avoid the main memory access and all. And anyway, the hit time will provide less overall impact and all. So the L1 and L2, the way they are will be, L1 should be smaller, and the block size of the L2 should be larger than the L1 and all. So this is like obvious things because of their inherent sizes and all. Right. So therefore, basically the L1 cache will be designed such a way that the access time should be as minimum as possible, and L2 cache should be such a way that the miss rate should be minimized here, so that it will not go to the avoid the access of main memory end. So these are the various considerations when you are going for multi-level caches. Okay, so the next one is that so far we discussed about in a cache, in a memory hierarchy, the top two level the memory structures we have discussed. One is the cache memory, and other one is the main memory. And in between the cache and the main memory, you have other levels of cache also can be there for achieving a better performance and all. And now here we are introducing, we are adding one more hierarchy to the main memory, that is below the main memory. So it's known to be a secondary memory or a disk storage. And here, when you add this disk storage, like another hierarchy to a memory, to a primary memory and all. So now in this scenario, the primary memory acts as a cache to the disk storage, We have main memory. So far we discussed about main memory and cache memory, and we are assuming that whatever the CPU refers, CPU access, CPU want, it will be present in a cache mostly. And if it is not present in a cache, it will be present in the main memory. So that was the assumption and all. It means that the entire program will be present in the main memory. But in reality, it's not so, because sometimes the programs are much larger than the size offered by the main memory or the main memory size and all. So in that case, you cannot accommodate, you cannot place the entire program into the main memory and all, right? And not only that, because our systems right now, they support the multi-programming or multitasking environments and all, or the multiple users may use the same system. So in that case, the memory should support, or memory should provide a multi-programming or multitasking environment. It means that multiple programs will provide access to the CPU, because one after another and all. So therefore, it means that the main memory will contain the multiple programs, multiple user programs, not one single user program, right? So in that case, also we require a concept of another memory, bulk memory, compared to the main memory. It should be there, where the entire the program, all of them should be available, will be available at the hardware, at the hard disk, or you can say that the disk storage and all. So in this context here, the main memory will be used or will be treated as a cache to the secondary memory and all for the secondary storage, right? And so this will be managed by CPU, hardware, and the OS together. The kind of the way of address translation from the like virtual memory, from the disk storage to the primary memory. So these will be carried out by using the address translation will be carried out by using CPU, hardware, and the operating system and all. And yeah, as has seen that programs share the main memory, as I already mentioned that. So there will be multiple programs will be placed into main memory. So which provides environment of multi-programming or multitasking environment and all. So in that case, the CPU will execute one program, and after that, it will go for next program in a time sliced manner. Or sometimes, no, when the program needs the IO and all, so at that time the program will wait for IO, and the CPU will pick up the next program. So for that purpose, the main memory should contains the multiple programs and all, multiple programs, right? So in that case also, programs in a main memory will not contain its entire code there and all. Only a portion of the program will be there in the main memory for its execution, and the rest of them and the entire program, the actual entire program will be there in the disk storage and all. Depending on the requirements, a segment of a program will be placed into main memory and it will be executed. And then once if it is over, then we'll bring the next segment. So that way, the code of the program will be like placed back and forth between the main memory and the secondary memory and all. And here in this context, for the main memory and the secondary memory, where the terminology will be slightly different. Where in case of main memory to cache memory, we call the information transmission, the information transfer, or you can say that the amount of the unit of information transfer between the main memory and the cache memory. So that we'll call it as a block, where the block contains the words, and the words further will be bytes will be there, right? Whereas here in the context of virtual memory, you can say that main memory to the secondary memory. So here the units are the terminology will be, instead of block, here we'll call it as a page. We call it as a page. It means that the amount of information or the unit of information that will be transferred between a main memory and a secondary memory will be in the form of pages and all, because the page have a much larger size compared to a block. So we have seen that the block size will be starts from a word, and it will go up to the multiple words like 4 words, 8 words, 16 words, 64 words, something like that, right? So that will be the block size and all. Whereas the page size will be of order of 4 kilobytes, 2 kilobytes, 8, 32, 64 kilobytes. That will be the order of the size of the page and all, size of the page. Because if you see that the size of the cache memory and the size of a main memory, their relative sizes and all. Like the cache memory size will be order of kilobytes or megabytes, whereas the main memory will be in terms of hundreds of megabytes, something like that, right? Or gigabytes right now. Whereas if you see the size of the main memory to the secondary memory, the size of secondary memory will be an order of hundreds of gigabytes, or like you can say the terabytes in the order of, whereas the main memory will be order of gigabytes or hundreds of megabytes. So therefore, for transferring the data between the main memory to secondary memory will be considerably larger one, much larger block, known to be pages and all, page. And similarly, the other term known to be miss, the term, the miss, that is between the cache and the main memory. So the terminology is a miss. Like suppose if the desired instruction or a data, if it is not there in the cache, they will say that it's a miss in the cache. And then we had to fetch from the main memory, and then we had to supply that. We had to place it to the cache memory. And here, this term, the equivalent term for this, the miss will be here, not to be page fault and all, page fault. It means that when the CPU requires a particular data item in a physical memory, and that should be there in a particular page. Suppose if the page is not present in the physical memory, then we say that a page fault is there, page fault occurred. It means that the desired data, the desired instruction is not present in the main memory and all. So therefore, we say that instead of miss, we say it's a page fault. That page is not present because the page size may be 4 kilobytes or 8 kilobytes, whatever. The page is not present. So we had to replace, or we had to fetch that page from the secondary storage to and place it into the main memory and all. Right. And the concept of why the pages here are used is, one thing is that, as I mentioned, that the size of the main memory and the secondary memory, their size will be very much different from. Excuse me. Yeah. So their size will be much different from the cache to that one. Another one is that the access time is also very different. If you look at the access time of the cache and main memory, like if you look at cache will be about nanosecond, and it will be about hundreds of nanoseconds. Whereas in case of secondary storage or disk storage, if you see the access time of disk storage is much, much larger, almost like 10 power 5 times difference between the main memory and disk storage. That means, assuming that the main memory access time is about hundreds of nanoseconds, whereas the access time of a disk will be like millions of nanoseconds, you can say, or much higher than that one. That means almost like 1 lakh times more than the access time of a main memory and all. So that is the order of difference. So therefore, when you try to access, when you need to fetch the page from a secondary memory to a primary memory, instead of going for a blocks and all, you have to fetch for a much larger unit, so that the misses will not occur, so that the page fault will not occur. Because when you're bringing a larger block of like 4 kilobytes or 8 kilobytes and all, so therefore it accommodates a lot of spatial spatial locality. So with that, there won't be immediate misses will not occur and all. So that was the reason that when you're fetching something from a disk, so you have to fetch much larger unit compared to the higher hierarchy, like fetching from main memory to the cache and all. And because the cache size is also smaller, and here the main memory size is reasonably larger in terms of gigabytes and all. So therefore, you can able to go for much larger size of the unit, information unit. You can able data can be transferred from from a secondary storage to primary storage. Right. So these are the various reasons for using the page and the related things. And now we'll see that how the address translation takes place here. And here the address translation, because the whatever the programs that are stored in the secondary storage, so they have their virtual addresses, as we have seen that when you're compiling, when the high level program, when it's compiled, and the executable, when you store it in the secondary storage, so it will be stored in the based on their like virtual addresses and all. And so now here these virtual addresses, that is nothing but the addresses that are that's where the executable program is present in a disk and all. And now when the CPU want to access that program, want to run that particular program, so first of all, it should be present in a main memory, because CPU can access up to the main memory. It cannot go beyond that. It cannot access the disk at all. It can access the cache, and if it is not there, then it can able to fetch from the main memory. So it can able to access the memory. So it cannot go beyond that. So therefore, the CPU for accessing the program or instructions and all, so it should get a physical address. But the CPU, first of all, the program is there in the virtual address. So therefore, CPU generates the first virtual address, and then the program will be loaded into physical memory, and then you will get corresponding physical addresses and all. So it means that to access the content, actual content of a process, a program, you need to have a physical address is required. But the actual address that is available generated by the CPU will be like virtual address. So therefore, there should be a kind of a mapping between a virtual address to physical address that is required, because the actual program, when it tries to access by CPU, it is available at a main memory, but it is actually resides in the disk. So that when it is reside in the disk and all, it is addressed by using its virtual addresses. So therefore, when the CPU runs this particular process, so it has to access from the physical memory or a cache and all. Both the physical memory and cache, they are accessed by using physical addresses. So therefore, there should be some address translation or address mapping is required from virtual addresses to physical addresses and all. So here, so therefore here you can see that here the way the translation will be carried out will be here. This is your virtual space. That means the program and the virtual addresses. These are the virtual addresses. And then when the program is running at that time, a part of a program may be present in the main memory. And then anyway, however, the entire address, the entire virtual space, virtual address is all the entire program executably, however, is present in the disk also, but part of it is present in a main memory and all. Main memory. So therefore, you can see that this is the total address space of a program, virtual address space. And this total address space will be some of them, some of these pages or some of these program content is present in the main memory. And the other portions are anyway, they are present at the disk and all. And now we need to find out actually for the given virtual address, whether that particular content or particular page, whether it's present in the physical memory or not, that we have to find out. If it is a present, then that can be accessed by CPU and the instruction execution will take place. If it is not present, then it has to be brought from the secondary, from the disk to the physical memory, and then it will be accessed and the instruction will be executed. So it means that actually, first of all, we need to have this address translation has to be carried out. So first of all, this is your virtual address space, like CPU generates the 32-bit address. It is your virtual address. And in this virtual address, as I mentioned that this program or that here this entire program is organized, is placed into your disk in the form of pages. In the form of, here page is nothing but assuming that page contains here 4 kilobytes. It means that 12 bits are used to represent the page, the byte within a page and all. Like, so suppose, for example, your program size equals to 1 megabyte, for example. So that 1 megabyte of program, executable program, is present in a disk, in the storage disk and all. And that is stored in the form of pages, in the virtual pages and all. And here each page will be like 4 kilobytes. So therefore, 1 megabyte of your program will be fitted into that many number of pages. 1 megabyte means it's about how much? 2 power 20. 1 megabyte means 2 power 20, right? 2 power 20. And one page contains 4 kilobytes. It means it is a 2 power 12. So therefore, to accommodate this 1 megabyte of program, executable program in a storage, it requires 2 power 8 pages and all. 2 power 8 pages. 2 power 8 means 256 pages, right? So the program is accommodated 256 pages. And now when the program to run, so actually here we had to, in principle, all these 256 pages has to be brought into the main memory. Then we have all these virtual addresses are corresponding physical addresses and the program will run smoothly. But as I mentioned that main memory cannot accommodate or cannot place the entire program in its in the main memory, because it also has to accommodate all the other programs also. And so therefore here out of these 256 pages, maybe like initially it may bring some 10 pages, and then those 10 pages are present in the physical memory, and all 256 the entire virtual, all the actual original executable, entire thing will be there in the disk at all. So now here there is here out of these 256 pages, there are 10 pages that are present in the main memory, and all others are there in the disk storage and all. And here, how do we know that actually here which of these 10 pages are present in the physical memory and all? So therefore, the CPU when generates a virtual address, we should be known that whether these pages are present in physical memory or not. If it is present in physical memory, then they can be accessed, and they can be, from that the instruction will be fetched and the CPU will execute those instructions. If it is not present, then the page fault will occur. Then that page will be brought from the secondary memory to the primary memory, and then the instructions will be executed and all. Right here, the way address translation takes place is like this way. Like suppose the CPU generates a 32-bit address, and if the page size equals to 12 bits, so the higher order 20 bits indicate the virtual page number. The higher order 20 bits indicate the virtual page number and all. Virtual page number. And now these virtual pages will be translated to the physical pages and all. So here in this case example, as I mentioned, assuming that a program contains 256 pages, out of that the 10 pages are there in the physical memory, that is accommodated by the memory and all. So it means that out of these 256 pages, so the 10 pages are there in the physical memory, and the remaining are anyway present in the disk and all. So here these 10, which of these 10 pages of this virtual page numbers are present in the physical memory. So therefore here there will be a kind of kind of mapping will be there, where for the given virtual page number and its corresponding physical page number and all. So if the virtual page number is present in physical page number, then we can access that particular page. That means the instructions in that page will be accessed by the CPU and it will be executed. And if the virtual page number is not present in the physical page, so it means that the corresponding page is not present. So therefore, if the CPU needs that particular page, so since it is not there in the physical memory, then it means it results the page fault. Then it has to be brought back. It has to be brought. It has to be fetched from the disk, and then it can be executed later on. So what I'm saying here is that there will be a translation mechanism, that maybe there will be a kind of a mapping from virtual page to physical page, and to hold this mapping for every process, will maintain a known to be a page table that I will show you here. We'll maintain a page table, like the page table will be something like this, and this page table maintains the, like it contains the, for every process we have one page table will be there. And in principle, if you look at here, if a CPU generates a 32-bit address, out of that the 12 bits will be a page offset, and remaining 20 bits will be your page number and all. So therefore, in general, for every page table should accommodate these 2 power 20 pages. Sometimes the number of pages, the process may contain much less than that. So, but here, since the CPU generates the 2 power 32-bit addresses, so therefore it can able to, with this 32-bit address, we have 2 power 20 virtual addresses, virtual pages are possible, right? And these 2 power 20 virtual pages has to be mapped to by using a page table, and this page table contains that it contains the physical page number. If it is present, if the virtual page is present in the physical memory, then it contains the corresponding page number, corresponding physical page number and all. If it is not present, then there is a bit used to be there here, one bit in the page table, and this is the most significant bit, and this is the valid bit. So this valid bit indicates that if the valid bit equals to 1, it means that the page table, whatever it carries, it contains the physical page number. It means that that particular virtual address is present, virtual page is present in the physical memory and all. If the valid bit equals to 0, it means that that particular whatever the virtual page number, it's not present in the physical memory. Instead, actually here it provides the disk location where the page is present and all, where this particular page is present. So that way here for address translation, for mapping, for every process, for every program, right? For every program, there will be a page table will be there, and that page table will map the virtual page number to its corresponding the physical page number and all. And here, based on this particular addressing mechanism, the 32 bits and a page size of 4 kilobytes, there are possible 2 power 20 virtual pages are possible. And these 2 power 20 virtual pages, that means to accommodate that, the page table size also should be 2 power 20. Out of that, there may be like many of the entries will be non-valid. Only few pages may have a valid entries. It means that they are present in the physical memory, and most of them are non-valid, because suppose for example your process size, your program size itself is very small, for example. So in that case, actually here most of these virtual addresses may not present at all, may not exist at all, right? So therefore here the page table used for mapping the virtual page number to physical page number and all. And so this will be carried out by this mapping, or this kind of the page table entries are filled up or will be done by the your this one the like the operating system and all. That means whenever a program has to be run, so this has to be placed into the memory, and then when whichever the pages they are placed into the memory, and those pages will be updated in the page table, and accordingly the bits are set, valid bits are set, and then this page table is also placed in the memory. And then whenever the CPU generates a virtual address, then by using this mechanism it finds the corresponding physical address, and then with that physical address it can able to access the desired page and all, right? So this way the page table will be used for mapping the virtual addresses to the physical addresses and all. And the page table, the creating the page table, updating the page table, so these things are carried out by the operating system and all. We'll see that later on in the next later lectures and all. We can able to see how the operating system will update, will maintain these page tables and all these things. We'll see later, right? So here come to this one. Yeah, you can see here, this is your like kind of this one. This is your virtual space, virtual addresses. All these virtual addresses will be, some of them will be placed into physical memory and some of them are not. So all this history, the entire details of these virtual addresses will be placed in the, you have, it is present in a page table and all. So for that purpose, whatever the virtual address space is there, for all this virtual address space, that means for every virtual page, there will be entry in the page table and all. And that entry will be either valid or non-valid. Valid means that particular entry where that particular page is present in the physical memory. And if it is a non-valid means that page may not is not present in the physical memory sometimes. And sometimes no, if it is non-valid means if even that particular virtual page is not exist at all. Because if the program size equals to smaller, then in that case 2 per 20 pages may not exist for all programs and all. For few programs where the page size is large, where the program is much larger, in that case it can accommodate entire virtual space, virtual address space and all. But in case of smaller programs and all, where that many pages are not required, that much space is not required. So in that case, that the page table will be mostly sparse. It may have only 10 pages may be there. Remaining all other pages will be simply they're non-valid at all. Right? So this way the address translation will take place, and then the page fault penalty. So page fault means if the desired page, if it is not present in the main memory, then we can say that a page fault occurred. So for handling the page fault here, because it takes about millions of cycles, millions of clock cycles it will take. So therefore here here in this case it can be accommodated, can be carried out by using operating system OS software, using software. Whereas if you look at here from in the cache and main memory, if there is a miss in the cache, so the desired the desired word or desired block will be fetched from a main memory to the cache. It will be carried out by using hardware automatically because it should be faster. Whereas here, in this case, to go for a disk access, and we know that the hard disk where it contains the spindle and have a magnetic disk and have a head rotation, there are mechanical components are there. So therefore, even though the transfer time may be faster, but to fetch the data from a disk and all, it takes a lot of time because there are a lot of mechanical components are involved in addition to the other electronic components and all. So it takes very huge amount of time. So therefore here use the operating system will be involved for fetching the page from a disk to the main memory and all, disk to the main memory. And we'll try to minimize this page fault as far as possible, because for every page fault it requires a huge amount of time, order of in terms of milliseconds. Whereas if you look at the miss rate will be for miss penalty will be order of in terms of nanoseconds, like hundreds of nanoseconds, whereas here in terms of milliseconds. So that way you can able to imagine what is the penalty here in case of page fault and all. So to minimize this page fault, we can use the policies like a fully associative placement that we have seen in the case of cache and main memory also. To reduce the miss rate and all, we can use the principle of fully associative. It means that it will reduce the replacements, the page replace like the block replacements and all. So that way the fully associative can be used. Here also can use the same principle. We don't use like a set associative or like a direct mapped and all, because we had to minimize the miss rate. So therefore the replacements has to be minimized. So therefore the fully associative placement will be used. And then the smart replacement algorithms can be used. The smart replacement algorithms will be used, and that will be supported by the this operating system will use the smart replacement algorithm. So with that, what happens is that, so we'll try to pick up a page which is very not at all required in the recent future and all. So that particular page will be picked up and it will be replaced and all. Right. So to minimize the page fault, there are two things. One is that like a fully associative principle, and second one is that the smart replacement algorithms can be used. Right. Okay. And then, yeah, you can see that, yeah, the page table, as we have already seen, so it stores the placement information. It means that for the given virtual address, virtual page, if it is present in the physical memory or not, so that will be indicated by the page table. And so array of page table entries are indexed by virtual page number. I will tell you what it means here. And there will be a page table register will be there in the CPU, and that page table register contains the address of the starting point of the page table and all. Because the page table is nothing but again the sequence of the memory locations where it contains the page numbers. It contains the physical page numbers or the mapping physical page numbers and all. So therefore the page table itself contains some information providing the details about the physical addresses corresponds to the virtual the page numbers and all. And so therefore this page table is also present in main memory, and the address of the page table will be placed in the page table register, and this is available in the CPU. One of the registers will be maintained the page table register. It means that, as I told you, that for every program, for every task, for every process, there will be a page table, will be specific page table, and that particular page table starting address will be placed in the one of the registers known to be page table register and all. So whenever the CPU generates some virtual address, then based on this, the page table register contents will first fetch the page table of the corresponding process. And from the page table, we'll try to find out that whether this particular virtual address is present in a physical memory or not. If it is present in a physical memory, then we can access that. The CPU can access, it can execute that. If it is not there, then the page fault will occur. And then as per the page fault, the page will be brought to the physical memory later and it will be used. Right. And then if the page is present in a memory, then the page table entry stores the physical page number. And along with this page, it also contains some other control information like a reference bit, dirty bit, and so on. You know that what is meant by dirty bit. Suppose in the process, the page in the one of the some of the instructions, some of the data of the page is modified, then it will be indicated by page is dirty. It means that a page has been modified. Because now you can see that page is now present in the main memory, and the same page is also present in the secondary memory also. And to maintain the coherence between these consistency between these two pages and all, we make use of the dirty bit. Whereas in case of cache and main memory, you have other policy, write through policy is there. But here that policy will not work here, because as we know that to access a disk, it takes about huge amount of time, millions of cycles as required and all. So for every write into a page, you cannot do it parallelly in the disk is not possible. So whenever you need to replace the page at that time, if the page is dirty, if the page is modified, then you have to store that modified page into the disk, and then you have to replace that. So for that purpose, the dirty bit will be used. The same purpose as that of the dirty bit that is used in between the cache and main memory. And there is a reference bit. The reference bit is used to indicate that how many times the page has been used, or whether page has been used or not, whether the page has been used or not, because this is used for replacement policy. Suppose, for example, for a particular process, you brought 10 pages, and when the process is executing, the CPU is not access all the pages, and it might have access to only first 5 pages, right? Or maybe some of the 7 pages, maybe remaining 3 pages it is not accessed at all, right? But later it needs, when it's continuing the processing, it requires some other some instruction or some memory address which is not present in the physical memory. It means that it requires some other page which is not present in the physical memory, but that has to be brought into the main memory, right? So in that case, what it will do, it is accommodated 10 pages, but some of the pages are not used at all. So therefore, it can replace those pages. For that purpose, this reference bit is used, right? So that way, this control information is used. Okay. And another thing is that actually here, this page table, as I mentioned, this is like 2 power 20 locations, or 2 power 20 like entities will be there. And then based on this virtual page number, directly the page table will be indexed by the virtual page number and all. Suppose the virtual page number equals to 20, for example, assume that. Then directly this virtual page number, we know the starting address of this page table, right? And then we know this virtual page number is 20. So therefore, the 20th entry will directly go to the 20th entry, and then we'll check that whether the valid bit is 1 or not. If the valid bit is 1, means this 20th page number 20 of this virtual page is present in the physical memory. If it is not, if the valid bit is not, if the valid bit is 0, it means that that page is not present here and all. That page is not present here. It means that page may be there in the disk, and then whatever the information that is available, with that you can able to access that. So likewise, that page table will be accessed by using virtual page number as an index and all. So that's why in principle the page table size will be like order of like whatever the virtual number of whatever the number of pages are there, virtual pages. So that is the length of the page table, and simply based on the virtual page number directly goes to that particular entry index, and then you can able to find whether the page is present or not. So that way you can able to access the page table. And anyway, the page you will get here in this example, you can see that there is a 32-bit address. So therefore 2 power 20 virtual pages are there. So therefore these 20 bits are used for indexing this page table, right? And then maybe that actually your main memory can provide only, the main memory can able to accommodate only 2 power 18 pages. 2 power 18 pages. So because of that, here the page table, the physical page number is only with 18 bits only with 18 bits. That depends actually. Suppose the physical memory is much smaller, because 18 means 18 plus 12, that is total 30 bits. It means that the physical memory size equals to 2 power 30 bytes. It means that it is about 1 gigabyte, 1 gigabyte of physical memory, right? 1 gigabyte of physical memory, where it can be able to address using 30 bits. So in that 30 bits, we know that the page size equals to 4 kilobytes. So therefore, remaining 18 bits will be your physical page number and all. So if it is a 1 gigabyte, suppose for example, if it is a 256 megabytes, then it's a 16 only, right? Here the physical page number will be accommodated only 16 bits. So that way the physical page size, that depending upon the main memory, the size of the main memory and all. So that way you can able to translate the virtual address to physical address and all. Okay, so now yeah, it's almost like 1 o'clock. So we'll stop here, and yeah, I think another 10-15 minutes will take for completing this virtual memory. So that we'll do it in the next class tomorrow. Okay, and then we'll start the operating systems, continue that. So we'll stop here at this point, and so so any questions on this virtual memory? And anyway, don't worry much about this virtual memory. These things we also discuss in the operating systems also. When you're discussing about memory management and all, we'll discuss about one complete chapter about virtual memory itself. And there also some of these things will be repeated over there. Because you can see here, when you're talking about virtual memory, the role of operating system will be coming to the picture. Because the reason is that, because see that if any page fault occurs here, you can see that the page fault occurs that to bring the page from secondary to main memory and all, we'll make use of we use the operating system. We take care of the service of the operating system and all. And at the same time, we have page table also. We have mapping these page tables and all. Page table size is also very huge. So for for handling those page tables and all these things also, mostly we use the operating system services and all. So that's the reason that. So when you are dealing with the virtual memory, that is a secondary storage to the primary storage in between the data transmission or whatever. So in that case, mainly operating system will play a role. Lot of role, more activities will be carried out by operating system. So that's the reason that we will discuss these things more thoroughly in operating system concept. Anyway, in the next class, we'll discuss a later part of this. Okay, so we'll stop here. So let me stop the recording. Okay.